Okay, welcome to the example lecture this week. So today I thought we'd solve a practical problem using the Laplace transform method. So it's going to be a spring mass problem. Okay, so we're going to look at a spring mass problem, but in this particular type of spring mass problem, we're going to have a unit impulse external force. Okay, so what we're going to do is we'll write down the ODE. So I'm going to say it's a spring with a mass attached to it with mass equals 1 kilogram plus 3 times y prime. So the damping coefficient beta is equal to 3 here, plus 2 times y. So the what do we call that? The spring constant is equal to 2 in this situation. And my external force is going to be this Dirac delta function at t minus 1. So what this means is that at time t equals 1, we apply a force to the system. And it's just an impulse force, so this is not a force that we're constantly applying. This is just a force that we apply once very quickly. Okay, so that's what this unit impulse represents. And we're going to say initially the system is at rest. Okay, and that gives us some initial conditions because it says that if the system is at rest at time t equals 0, the position of the mass is at y equals 0, and the velocity at t equals 0 is also equal to 0. Okay. So if I want to solve the dynamics of this system, the first thing I can say is, well, y of t equals 0 for t less than 1. Okay, and how can I say that? Well, initially the system is not moving, okay, and I do not apply any external force until time t equals 1. So I know, without doing anything, that the solution between t equals 0 and t equals 1 is y of t equals 0. Okay, but that's not a very interesting solution, so let's solve this ODE now using the Laplace transform method. So I'm going to take the Laplace transform of each term here. So the Laplace transform of y double prime, if you recall, is equal to what is it? S squared times capital Y of S minus S times the first initial condition minus the second initial condition. And of course both of these terms are 0 because our initial conditions are 0 for both initial conditions. So we quite simply get the Laplace transform of y double prime is equal to s squared times y. And similarly the Laplace transform of y prime, it's not too hard to show that this is just simply going to be equal to 3 times s times y of s. The Laplace transform of 2y, let's write that a bit neater. The Laplace transform of 2y is just 2 times y of s. And then finally, the right hand side, the Laplace transform of this Dirac delta function here, Laplace transform of Dirac delta of t minus 1. Okay, well that's just going to be equal to e to the minus s. Because t naught is equal to 1, so we just get e to the minus s times t naught, or e to the minus s. Okay, so writing that into our differential equation, I can pull out a common factor of y actually, and write this as s squared plus 3s plus 2 is equal to e to the minus s. Or in other words, I can say y of s, my solution in terms of s, is equal to, well, let's write this as 1 over s squared plus 3s plus 2, all multiplied by e to the minus s. Okay, but the denominator there, I can write that like so, like this. I mean, okay, I can write this as 1 over s plus 1 s plus 2 times e to the minus s, right? So just turning that quadratic into a product of two linear factors. Okay, and then this thing here, this fraction here, I could use partial fraction decomposition to write this in a different way, right? So let's do that now. So 1 over s plus 1 s plus 2 is equal to a over s plus 1 plus b s plus 2. We're going to multiply both sides by this denominator here. So on the left hand side I simply get 1. On the right hand side I'm going to get, well, the s plus 1 is going to cancel. I'm just going to get s plus 2. And similarly for the b, the s plus 2 is going to cancel, and I'm just going to get s plus 1. So now let's substitute in s equals negative 1, and then I get, that gives me 1 is equal to, well, if s is negative 1, negative 1 plus 2 is 1, I get a is equal to 1. S equals negative 2, well, again on the left hand side I still get 1, the a term cancels, and I get negative 2 plus 1 is negative b. So I get b is equal to negative 1. So therefore I can rewrite my solution y of s as a, which is 1 over, which one was a? S plus 1 minus 1 over, what was it, s plus 2, wasn't it? S plus 2. And that was all multiplied by this exponential of minus s. Okay, so I want to find the solution in terms of y of t. Okay, so now I have to, well, that is equal to the inverse Laplace transform of y of s. Okay, so let's just split this up. Let's have a look at what is the inverse Laplace. Okay, let me just write this like so. F of t is going, I'm going to call that the inverse Laplace transform of 1 over s plus 1. Okay, well, what is this? This is quite simply e to the minus t, right? In fact, let's call that f1 of t. f2 of t, let's look at the inverse Laplace transform of 1 over s plus 2. Well, again, that's just going to be e to the minus 2t. So if I did not have this exponential term here, the inverse Laplace transform of y of s would just be some linear combination of these two exponentials. But I do have this e to the minus s here, so what I have to do is I'm going to have to use the second translation theorem. Okay, so the second translation theorem, remember, is a way that we shift the solution in the t domain. Okay, so let's just write down what that second translation theorem is. So how does it go? Laplace transform of f of t minus a times the unit step function at t minus a is equal to e to the minus as times f of s. Right? Okay, so in our case, this a in here, this is equal to just 1, right? A equals 1 in our case. So what I want to do now is evaluate f1 and f2 at t minus 1. f2 equals f2 evaluated, sorry, at t minus 1. Okay, well, f1 is e to the minus t, so f of t minus 1 is e to the minus t minus 1. And similarly, f2 is e to the minus 2t, so f2 evaluated at t minus 1 is e to the minus 2 t minus 1. Okay. So now I can use my second translation theorem to evaluate the inverse Laplace transform of capital Y of S. So maybe let's just write that down again. So we get, well, let's write it like this. E to the minus S over S plus 1 plus E to the minus S over S plus 2, right? The inverse Laplace transform of Y of S is going to be E to the negative t minus 1 times U t minus 1. Sorry, minus, shouldn't it be? This should be a minus here. Minus e to the negative 2 t minus 1 times u of t minus 1. Okay, and so this is equal to y of t. The solution y of t is equal to e to the minus t minus 1 u of, in fact, let's pull out that common factor of u. That u of t minus 1 times e to the minus t minus 1 minus e to the minus 2 t minus 1. Okay. Interestingly here, this unit step function here, this is equal to 0, so this bit equals 0 for t less than 1. So this is exactly what we said at the start of our of this problem, is that this mass spring system will not move. It will stay in its rest position until we apply that impulse that at t equals 1. So this is actually coming out in the solution here, which is really encouraging. So I could write this solution y of t. Okay, also note that this unit step function equals 1 for t greater than or equal to 1 as well, right? So I can write my solution as 0, y of t equals 0 for t less than 1, and equal to e to the minus t minus 1 minus e to the minus 2 t minus 1 for t greater than or equal to 1. Okay, and in fact, if you wanted to plot this, it looks something like this. So this is t, this is y. It looks something like 0 down here, and it pops up and then decays. So this is t equals 1 here. So the system does not move until we apply that impulse, and then it spikes and then decays down because it is damped, a damped system. So this really kind of interesting problem here, where we have a mass spring system at rest and just apply an impulse to it. This could not have been solved using any method we've learned in class, apart from this lovely Laplace transform method with the second translation theorem here. So I hope that's clear, but if not, please feel free to get in touch. And okay, now I'll move on to solving a problem using Octave or well, I'll use Octave Online. Okay, so I'm on Octave Online here, and I just wanted to show you that Octave actually can calculate the Laplace transform and also the inverse Laplace transform. Unfortunately, the Octave Online version can be extremely slow. So really, using the online version of Octave, we can only take the Laplace transform or the inverse Laplace transform of fairly simple functions. Okay. Well, let's try something here. So first thing we need to do is create symbolic variables s and t. So sims t and s. So that will give us these two variables. And now to calculate the Laplace transform of a function, we just type Laplace. Well, let's just try the Laplace transform of t squared. And so you may need to add extra time down here because it can take a while, but okay, here we've got the Laplace transform of t squared is 2 over s cubed, so that seems correct. How about the Laplace transform of t times the exponential of, let's say, negative 2 t, negative 2 times t. Let's see if Octave can do that. Okay, so fantastic, it seems to be able to calculate that. Okay, what about the inverse Laplace transform? So the command for that is Laplace, Laplace, so inverse Laplace. Let's say 1 over s squared, so that should be t, so let's see if that correctly calculates that. Now let's try something a little bit more challenging now. Let's say s, well, plus, let's say s minus 2. 1 divided by s minus 2 squared. Let's see if it can calculate the inverse Laplace transform there. Fantastic. So using Octave Online, we can actually calculate Laplace and inverse Laplace transforms. I also just wanted to point out that Wolfram Alpha can do the same thing. So let's look at Laplace transform of 2 times t cubed and see if it can calculate that. So it gives us 12 over s to the power of 4. So that looks correct. And let's just check the inverse Laplace transform of, well, let's go 1 divided by s minus 2 squared again. Let's see if it can do that. Okay, and it gives us the correct answer there. So using these online tools, we can actually calculate Laplace and inverse Laplace transforms for simple cases. So that is definitely worth knowing. You can also check your assignment solutions, for example. And one more thing that may be interesting is to do with partial fractions. So Octave can in fact calculate the partial fraction decomposition for a function. So, and the command for that is partfrac. So partfrac, let's do the ratio of two things. Let's calculate the partial fraction decomposition of negative s squared plus 5 times s plus 17. So you may recognize this problem from lecture 25. Okay, and then over s minus 1 times s minus 1 times s plus 6. So let's see if it can calculate the partial fraction decomposition in that case. So in fact, quite rapidly, it was able to calculate this. So negative 1 over s plus 6 plus 3 over s minus 1 squared. So you may recognize that that is exactly the solution that we got in the lecture 25. So using Octave, you can, and in fact it also works for Wolfram Alpha, we can actually calculate the partial fraction decomposition of some functions. Let's see if it will. Let's see in Wolfram Alpha, partial fractions of that thing. Let's see if it works. So sometimes, there we go, it works. Sometimes you can enter something in Wolfram Alpha that takes too much server time, so it won't work, but in this case it happily calculated the partial fraction decomposition for this problem from lecture 25. Okay. So finally, I'll just show you too that Octave can, and MATLAB as well, can actually account for these unit step functions, or if you recall, sometimes we call them the Heaviside function. Okay, so we do have the Heaviside function built into Octave. It's actually represented in Octave by this capital theta of t. So let's have a look if we take the Laplace transform of t minus 1 times the Heaviside of t minus 1. Okay, so this should be, okay, well, the Laplace transform of t is 1 over s squared, so this should be, and here we're using the second translation theorem, so this should be something like the exponential of negative s over s squared, or something like that. So let's just check. Here we go. Okay, so, well, it's not very pretty, but you can see that we've got exponential of minus s over s squared. So in fact, Octave can also calculate the Laplace transform of the Heaviside function. Let's try the inverse Laplace transform of this thing. So the exponential of minus s divided by s squared. Let's see if it can calculate the inverse Laplace transform for this case. And okay, it can in fact. So we get t minus 1 times theta of t minus 1, where theta is that Heaviside function there. So for fairly simple symbolic expressions, or let's say fractions, we can calculate the Laplace and inverse Laplace transform using Octave. Okay, so this is a good way to potentially check your results of your assignment, or just have a play and test out. Okay, great. So I'll see you in the next class.